Hello and welcome to our first tutorial about dynamic meteorology. My name is Kazungu from the University of Nairobi. I study BSc in meteorology. And when we talk of dynamic meteorology, we want to see how the air behaves in the atmosphere, how a parcel of air moves from the surface of the earth to a certain level. And when air moves, it is affected by basically three forces. That is the PGF, the GF, and the centripetal. So I want to learn how we can derive these formulas that or equations that will help us to solve the very things that we are talking about, like the pressure gradient force. So to begin with, I'll start to derive the formula for pressure gradient force, which in short I will call PGF, like that. So this is a force that is acting upon a parcel of air due to the effect or the difference in gradients. That is what you call the pressure gradient force. So we consider an air parcel, like if we consider that air parcel to be like in form of a cuboid, if we consider it to be in form of a cuboid, and maybe I'll draw it here, and we shall consider it into the 3D, that is in X direction, in Y direction, and in Z direction. And because we are considering the three dimensions, we shall also consider the change in time. So if this is the X direction, this will be the Y direction, and probably this will be the Z direction. And therefore, when air moves from one level to another, it has a small change in X direction, a small change in Y direction, and as well as a small change in Z. So we'll have a small change in X, which is the same to the other side, though opposite. We'll also have a small change in Y, and of course we shall have a small change in the Z, in the height. So if we say, like, if this is the center of this cuboid, if this is the center, so we'll have the coordinates x naught, y naught, z naught as our coordinates, because we are considering three dimensions. And at this point, we shall know that pressure is P naught, the initial pressure at that point. Now, if we are considering the difference in gradients, we shall have the difference in pressure in both directions. So we'll have the pressure gradient in the directions, that is, in the X direction, we shall have a partial change in P over partial change in X, which will give us the pressure change or pressure gradient in the X direction. In the Y direction, we shall have partial P, partial Y, that will be in the Y direction, and in Z direction, we shall have partial P, partial Z. So these are basically the changes in pressure in terms of the direction that the air parcel will be taking. Now, let us consider two sides. Now, these sides are from this cuboid. So consider these two sides or two faces which are opposite. So you can say maybe this is face A, and maybe the other one that is on the other side is face B. And these faces are they are in the direction of X, but they are in opposite direction. So that means if we get the magnitude of A, or the force that is acting upon the air parcel at face A, will be opposite to side B, just changing the negative sign, because they'll basically be the same. So if we consider those two sides, maybe we've said face A and B, so we'll have to derive the formula. So for pressure at point A, or at phase A, will be basically P of A x. I'll call it, for this tutorial we shall use that to represent the pressure in the x direction. And this pressure will be given by the initial pressure P naught. We subtract the partial change of pressure in the x direction, but we shall also consider a small change in the x direction, that is change in x, and we shall halve it to 2. We shall add on this should be like, if we say it's 1 over 1 factorial times that, this will also be plus 1 over 2 factorial, then partial change in P over partial change in x, but this will be now the second derivative, that is partial squared P over partial x squared, and then we have this over 2, and then we shall square it, plus, as you have so many changes in the direction. But as I said, that this, since this is very small now, since this partial is small, then we shall say that if we say like change in x raised to 2 will be nearly 1. So if we raise this to a power of 2 and higher, that means this value will be tending to 0. So we can neglect this part because it is too small. So we can neglect this. Remember, we've said that this small change in x is very small, and the more you square it, it will be very small. So it's better we just ignore it. So therefore, that means pressure in the x direction will basically be P naught minus, 1 over 1 factorial. Of course, 1 factorial is just 1, so it will just be change in P over change in x, small change in x over 2. So we can call this our equation 1. So this is, we've considered phase A. Now, we now want to get the force that is acting upon this air parcel at that point. From our basic physics, we know that pressure is equals to force over area. And we are interested in force. So we can now say from there that force is basically equals to the product of pressure and area. So what we'll have to look for is only the area, because for the pressure we already have it here. So we shall just look for the area, and of course from our cuboid, the area is length times width. So our area will be the length times the width. That will give us our area. So we'll now say that force that is acting upon this will now be pressure, which is P naught minus partial change in P over partial change in x, partial change in x over 2. Now we'll have to multiply this. We have to multiply it by the area, which is partial change in y and in z. So this will give us the force that is acting upon our air parcel at phase A. So we can call this equation 2. Now let's consider phase B. Now in phase B, we shall say pressure at phase B, basically pressure at B, x. Remember, it is in the x direction. So the pressure at that phase B will be given by the initial pressure, but now this will be, you're adding on. Remember, it is opposite. So it's just the change in the signs. So it'll be plus the partial change in P over partial change in x, then that over 2. Remember, we can add on 1 over 2 factorial the pressure change in x, but now this is squared, now like this. But we said that because the delta is too small, we can ignore this. We can ignore that. So we only remain with this as our pressure at that point. I mean, on phase B. Now, for our case, now force in the Bx will now be, remember force is pressure times area, and the area of phase A and phase B is the same. So you'll just say P naught plus that over x over 2. Now we multiply by our area, and our area is small change in y over small change in z, like that. So that will give us our force. We can call this equation 3. Now we have force in both phases, phase A and phase B. Now, to get the net force, we can call it maybe force Px. We'll now just say that force Px is equals to, we now take force at point A minus force at point B, or phase B. We have force at A, that is here, so we just lift it. So we say that force at that point, the net force is equals to P naught minus change in P, change in X over 2. Our area must be taken care of. Now we minus this force, which is P naught plus change in P over change in X, small change in X over 2. We multiply it by our area. So that will give us our net force. And of course, we shall open these brackets. So it will be force, our net force is equals to P minus that over, we just rewrite it, over 2. It won't change, over Z. So this is 1 minus, now this will be now P naught. This will give us minus change of P over X, small change of that, change in Y, change in Z. Now that will give us that. So we collect like terms, we find that this will give us 0, and if you multiply through by 2, we shall find that we are remaining with dx, small change in x. So our net force will result to be equals to, we'll have our negative partial change in P over partial change in X, small change in X, small change in Y, and small change in Z. So that will result, from here we get that this is our net force. Maybe we can call it equation 4. Now, what we have to note that we are interested in force per unit mass. So that means that we'll divide through our net force by mass. And from our basic mathematics, we know that density is always given by mass or volume. So from this, we now say that mass is density times volume. And from our case, if you look at our case, that volume is basically the cross-section area times the height or the length. So if we get back to what we've been doing, we can get, this is the change in X, change in Y, and change in Z. So it has scattered for both the sides. So we are right to say that our volume is basically change in X, change in Y, and change in Z. That will give us our volume. So therefore mass will be given by, remember it is density times volume, and our volume is change in x, change in y, and change in z. And we said that we need to get our force per unit mass. So we shall take our force at px divided by mass, should give us that will be negative change in p over x, change in z, x, change in y, and change in z. We divided by mass. So, but our mass here is given at that point, so we shall just replace whatever we have, and from that we shall find that it is force at px over our mass is rho, change in x, change in y, and change in z, is equals to negative partial that, change in x, change in y, change in z, over rho, change in x, change in y, and change in z. And we know that this will cross that, so we'll get, if we can let this, you let this be small f, maybe f px, can call it that way. So that will be negative rho, change in p over change in x, and this will just be like times 1 over rho. So for instance, we now, if that was question 4, this is question 5. So we say that now the pressure gradient, force in the x direction is given by this formula. So we've already found the pressure gradient force in the x direction. So pressure gradient force, which is just force px, that is in the x direction. The x direction is equals to negative 1 over that, change in p, change in x. So I said that the change in pressure in the x direction is the same throughout. Is only we shall only change the denominator. So we can just say similarly, the PGF in y direction is given by negative 1 over rho, change in p, change in y. And then also the PGF in the z direction is equals to negative 1 over rho, change in p, change in z. That means if you can be able to derive one of the formulas in one direction, you are able to derive the others, because it is basically the change in the direction only. So for this tutorial, we found that the pressure gradient force is dependent of the pressure, which is changing with the height, and as well as the density of that air will give us the very gradient, the pressure gradient force. After you've calculated the pressure gradient force in both x, y, and z, we can now represent that in vector form. So in vector form, it's just basically you are adding the three sides, the three dimensions. So our pressure gradient force will be negative 1 over rho, changing that x, and this will assign that it is the vector I, the unit vector I. Now it should be plus, but plus and minus will give us minus, so it will be just minus 1 over rho, change in pressure, change in y, and this will be in the j, and also we'll have 1 over rho, change in p, or change in z, and this is vector, the unit vector k. So from this equation we can see that it is the density varying with pressure. So you can basically represent it as the pressure gradient force is equals to -1 over rho and the change in pressure, or grad P, and maybe you can call this equation 6. So this is the pressure gradient force in vector form, and the others were pressure gradient force just in one direction, but this is in the 3D. So something to note before we conclude our lecture today, that from equation, which was equation 6, now from equation 6, remember equation 6 is F, the pressure gradient force, is equals to -1 over rho grad P. From this equation we can say that the magnitude of the force, and in this case is the pressure gradient force, which is Fpx. So the magnitude of the force depends on the pressure gradient, and our pressure gradient is grad P. And then we can look at the relationship between the pressure gradient force and the pressure gradient. So we can say that the bigger the gradient, the stronger the winds. Why? Because from here we can say that our force is directly proportional to the pressure gradient. So that means an increase in pressure gradient force, an increase in change in pressure will lead to a corresponding increase in pressure gradient force. So do not forget how to derive this. You can get it in either in x direction, in y direction, or in z direction, or you can get it in vector form. So may you catch up with us for other tutorials when we'll be deriving maybe the gravitational force, maybe the Coriolis force, maybe the centripetal or centrifugal, which are equal and opposite, in our next tutorials. But for today we were to derive the formula for pressure gradient force, and these are the 2 remarks that we've made after the class. See you in the next class.